Let's talk about robust regression. So what do you do if the errors are not normally distributed, especially if they have heavy tails and maybe there are even a lot of really extreme residuals? What do you do in this case? Well, you want to sort of minimize the contribution that these large residual valued observations contribute to the least squares or to the beta coefficients calculations. So here's a method called M estimation. M for Matt Jones, by the way. Just kidding. This method chooses the beta hat values that minimize this stuff right here. Now this is a Greek letter rho, and it's a function. Okay, so this is rho of all of this stuff. Notice what we have in here is this is the ith residual. Take the actual y value observed and then subtract the corresponding predicted value. That's the residual. And you're taking some function of this. Some common choices for rho would be, say, x squared. Rho of x equals x squared. In that case, you're taking the residual and you're squaring it. That's just regular old least squares. Remember, least squares is done when you're trying to minimize the square of the residuals. Or you could take the rho function to be just the absolute value function. This is called least absolute deviation, or LAD, or sometimes called L1 regression, because the L1 norm is defined to be the sum of the absolute values of the numbers in the vector there. Okay. There's something else that's called Huber's method. It's sort of a compromise. Rho of x in this case is taken to be x squared over 2 for whenever all the magnitudes of these x values. Remember, these x values here, for our purposes, they are the residuals. So whenever the residuals are less than or equal to some constant threshold, we'll take we're basically essentially doing least squares. We're dividing by 2, but it's essentially least squares. Otherwise, if x is larger than that, then we take it to be this constant, this threshold times the absolute value of x minus c squared over 2. So you subtract off this this larger amount here. So here c is some kind of robust estimator for the standard deviation of the residuals, such as maybe the median of the absolute value of the residual values. So this M estimation method is related to weighted least squares, by the way. Let's take a look at that. So if you remember, or even if you don't, the normal equations for least squares are given by this. That is, this is just what you get when you differentiate the squared errors, the sum of the squared errors with respect to the betas, and then you set to 0. Remember, and if this doesn't look familiar to you, just note that beta hat, remember, equals x transpose x inverse times x transpose y. So, if you inverse, take the inverse of this product here and move it over, then that's what you get. This is essentially how you get the beta hats. Now, similarly, the normal equations for weighted least squares look like this. Okay. It's exactly the same, except you got this inverse of the inverse of the variance covariance matrix appearing here and here. Okay, so or I can write this using summations. You can see I've crossed all this stuff off because I didn't. Well, it looks better this way, I think. Okay, this line right here is exactly this. This is just writing it with matrices. This is writing it with summations. Okay. So now, if you differentiate this M estimate criterion, so this M estimate criterion is up here. Okay. It's this stuff. This sum of rho of the residuals. Okay. I'm adding this up. So if I differentiate that with respect to each beta j and set to 0, then this is what you get, right? You get, it's the sum of, I'm taking the derivative of this is the quantity you want to minimize. So remember, the rule is if I can differentiate the sum by taking the sum of the derivatives, and then so how do you take the derivative of this function of all this stuff with respect to beta? It's the derivative of the function times the derivative of the stuff inside. So that's what I have here. It's the derivative of the function. They're evaluated at the residual times the derivative of the stuff inside, which, remember, this is a vector times a vector. This is the ith observation vector. Okay, what remains when you differentiate that with respect to the jth beta is just negative sign, the jth value in the ith x observation vector. Okay, so that's how you get that. Setting that equal to 0, you get this. Okay. It's just the same. Set this equal to 0. You can remove the minus sign. Right. So again, remember this stuff right in here is just the ith residual, and maybe let's set that equal to u sub I for now, just so that we can write it less complicated like. And yeah, what I can do then is if I multiply and divide by the ith residual, okay, again, u sub I is the ith residual. Here I'm expressing it this way. Okay. Here I'm just going to write u sub I like that. Okay. But note that these two things are really the same. If I cancel like that, then I actually have this stuff up here. This is the same, okay? But if I write it this way, then I can think of this the derivative of rho evaluated at ui over ui as some kind of a weight, okay, which I'll call w of u sub I. And then if I slide that in here, look at what you get. You get all this stuff, and so you think of, again, you want to think of this w as your weight function, but all of this stuff is in fact the same as what you get up here for the weighted least squares. So that's the connection between M estimation and weighted least squares. Okay, so so a few things here. W of u, if I let this be a constant in u, remember the u for our purposes are the residuals. If that's just a constant, then you get ordinary least squares. On the other hand, if I set w of u equal to 1 over the absolute value of the residual, then that results in LAD, the least absolute deviation, okay, method. Note then that what happens is the weight actually decreases as the residual increases, so more extreme observations have smaller weights, which is something that you might really want. Another common choice is something called the Huber method. W equals 1 for whenever the absolute value of the residual is less than or equal to some threshold, some constant c, which again, maybe you take this to be a robust estimator for sigma. And otherwise, for the residual, when the sizes of the residuals exceed this value, take it to be c over the size of the residual, so it diminishes. So this is a nice sort of compromise between least squares and the LAD method. You get that it's essentially operating like least squares when the residuals are not so large, but then the farther they get away, suddenly they sort of the weighting sort of drops off. Of course, there are many other potentially good choices for rho. It might really sort of depend on what kind of data you have, what's really going on there. M estimation can require significant computing time because it's carried out iteratively. You can see that if you think about it. The weights depend on the residuals, right? So the idea is you have to go and you get the weights. Once you have the weights, you can get the betas. And then once you get the betas, you can compute the residuals. But then once you have these new residuals, you can compute new weights because the weights are functions of the residuals. And then you get the betas again, and it's just here we go around in circles, a cycle there. You get standard errors using the weighted least squares. There are estimates for the variance of our estimators of our model coefficients. There will be some number, some robust estimate of sigma squared times x transpose w quantity times x inverse.